Let us unpack what the Chinese remainder theorem says for integers, a bunch of ideals in the integers. So I'll walk through this exercise, and in the process we'll see what it says. So here's a concrete question about arithmetic. Find all integer n such that when you divide by 4, they leave remainder 2. When you divide by 9, they leave remainder 5. And when you divide by 5, they leave remainder 3. As long as these moduluses 4, 9, and 5 are relatively prime, there always exists such n, and such n can be described using the Chinese remainder theorem. Let's first, so I still have the statement up here. It says that if you have a commutative ring R and a bunch of ideals m1, m2, mn in R, you let m be the intersection of this. So the key assumption is that these ideals are co-maximal, meaning the sum of any two of them is R. Then the intersection is same as the product, and R mod m is isomorphic to R mod m1 cross R mod m2 cross R mod mn. So in the situation of the exercise, the ring in question is Z, and there are three ideals, 4Z, 9Z, 5Z, correspond to this moduli. And because these numbers are relatively prime, 4, 9, and 5, these ideals are co-maximal, meaning 4Z plus 9Z is Z, etc. Same, 9Z plus 5Z is Z. And you can see that you can write 1 as a combination, right? Minus 2 times 4 plus 1 times 9 is 1. So if you can write 1, you can write any multiple of 1 as a linear combination. So these are co-maximal ideals. So what the Chinese remainder theorem in this case says is that this product is isomorphic to Z mod, the product of these numbers, which is 184 times 9 times 5. This is isomorphism. And now what the question is asking is that I give you a thing here, 2 mod 4, 5 mod 9, 3 mod 5. And can you find me a number here which maps to this? Okay. And the answer is yes, because these things are isomorphic by Chinese remainder theorem. By the way, this isomorphism is the statement of Chinese remainder theorem for integers. Okay? But to find this number or numbers, so there will be a unique number mod 180, meaning once you find one of them, you can get all of them by adding multiples of 180 to it. But to find one of these numbers, you need to see why this map is onto. Meaning, I think that's better to do in general. So let's say give you C1 mod M1, etc. C n mod Mn, where M1, M2, C1, C2, Cn are some elements of R. And you're asking, can you give me an element of R mod M which map to it? In fact, let's find an element of R that map to it. So the key observation is this. Let Ni be the product of all the ideals except the ith one. Then lemma, I claim that Mi plus Ni equals R. The proof of this I'll leave as an exercise now. We did. If you have only two of them, there is nothing to prove. That's the part of the assumption. So in general, under this assumption, so this is under the assumption, still assuming that they're co-maximal. Okay, I assume mi plus mj equals r for all I not equal to j. Then when you take the ith one and add to it the product of all the other ones, they're still comaximal. In any case, I won't prove this because this would be clear in our example. But if you grant me this, what does this mean? This means, so there exists AI in mi and EI in ni such that AI plus EI equals 1. Because 1 is in R, so that can be written as a thing from mi plus a thing from ni. Now you look at this EI and you ask yourself, what happens to EI when I go mod these ideals m1, m2, mn? Meaning, I have this map R to R cross m1, R cross mn, taking an element to its congruence classes. Mod m1, x plus m1, x plus mn. What happens to EI, let us ask? Well, when you take EI is 1 minus AI, and AI is in mi, so this is 1 mod mi. So in the ith place, you're going to get 1. And notice that take any other place, so in the first one, let's say I is not 1, then in the first place you're going to see 0 because EI is in ni, and ni is the product of all these guys, so this is in m1 and in m2 and in mn. It's in all of them except the ith guy. So because ni is in m1, when you go mod m1, you get 0. Similarly, you get 0 here, 0. So these EIs go to basically the 0, 0, 0, 1, 0, 0, 0. So like the unit vectors. That's why the name EI. So now, if you take the element, so if you take the element summation Ci EI, you can check that that goes to C1 plus M1 Cn plus Mn. I mean, this is a very easy check. So what you need to do is find these EIs. Let's see what that entails in our situation in the integers. So in our example, I have 3 things. M1 is some multiple of an integer, some m1z, mn is some mnz. Okay, and we let ni to be the product divided by the ith number. So what I'm calling ni up here is same as niz. Okay. What I need to do is I need to find, let's say, an integer ei, which is 1 mod m1 but mi, but 0 mod all the other ones for j not equal to I. Okay, so note that this ni fellow is already 0 mod all the mj's because it's a product of all the other mj's, you see. So ni fits this bill. And this ni is also relatively prime to m1 because I have divided by m1 and these numbers are relatively prime. So not ni is 0 mod mj for all j not equal to I and relatively prime to mi. So you can find ni bar such that ni bar is 1 mod mi. And this thing you can, because ni is relatively prime to mi, so it has an inverse mod mi. So this ni bar is going to be an inverse of ni mod mi. And you set ei to be this product. Now this thing is a multiple of ni, so it's 0 mod all the mj's if j is not equal to I, and it's 1 mod mi because I made it so. Now let's unpack all this in our example. So I is 1, 2, 3, and let's write down what these things are. Mi are the moduli, so it's 4, 9, 5. The ni's are the product of the other ones. So this is 9 times 5, 45. N2 is 4 times 5, 20. And N3 is 4 times 9, 36. What about Ni bar? Now to find the inverse of 45 mod 4. So 45 is 1 mod 4. 1 is the inverse of 1. 20 is 2 mod 9. So the inverse of 2 mod 9 is 5. Because 5 times 2 is 10, which is 1 mod 9. And 36 is 1 mod 5, luckily. So again, the inverse of 1 is 1. Yeah. So you see 45 times 1 is 1 mod 4. 20 times 5 is 1 mod 9. And 36 is 1 mod 5. So the EIs are the products 45, 100, 36. So now I can say what goes here. 45. So this thing, right? Summation CI, where our CIs are these guys, C1, C2, C3. So you'll get 2 times 45 plus 5 times 100 plus 3 times 36. That plus any multiple of 180, which if you calculate comes out to 158 plus 180z. So 158 is a number which when you divide by 4 leaves remainder 2. When you divide by 9 it leaves remainder 5, and when you divide by 5 it leaves remainder 3. You can check that. And all such numbers is given by that plus any multiple of 180. So that's our answer.